So let's take a look at the life of the stars. And if you're following in OpenStax, these are chapters 21, 22, and 23, although we won't cover everything in those chapters. So, stars have to start somewhere. They have to be born somewhere. And they're born from interstellar clouds. That means clouds between the stars. And they're called stellar nurseries. And one such stellar nursery that's kind of familiar is the Orion Nebula. So if you know the constellation of Orion, you might know Orion's belt here. Now, if we look at it in the visible light, that's what you or I would see in the night sky. But if we look at the infrared, we can see a lot of gas and dust there. And there's some spots that are cold clumps. And those are the cores. Now, what that means is it's a little colder, it's a little denser, and because of gravity is what gets the star started, it can start to attract the atoms and the dust in there. So here's the process. Gravity, so if we look at the interstellar dust cloud, here's the cloud. It can start to attract, and those clumps can attract each other and attract more atoms to the core. And then we have what's called a protostar. And it has a disk around it, which is going to be very important in our story here. We're going to look at from birth to death of the life. We're going to look at its whole lifetime. Now, when enough of the matter gets squeezed in, fusion can start. And as we talked about in the sun video, we can get the solar wind, and that'll sweep away some of the material. And that solar wind we're going to see sweeps it out from the cores, or from the poles here. And then we get a new star with that planetary disk around it. So what we can see here is we can see the gas jets coming from the protostar there. And I got to turn my pen on. Sorry about that. We can see the gas jets. And you can see this is over from 95 to 2000, over 5 years. It hasn't really slowed down. This is going to go on for a while. Now, a reasonable question is, well, why do stars spin? Because they do. There's natural turbulence out there in those dust clouds, so they have a little bit of an initial spin. But if we think about a figure skater, we can see our drawing of the figure skater. When she has her arms out, she'll be spinning slowly. But if you've ever seen a figure skating competition, when they tuck their arms into their body, they spin very, very fast. That's exactly like the star. When the star is very large, it just naturally spins a little bit because of turbulence. But as it contracts and gets small, it'll spin faster and faster. And that's called the law of conservation of angular momentum. And that's a law in the universe. It has to, if you're smaller, you have to spin faster. Now, at some point in the young star's life, it may form planets. And planets need elements that are heavier than hydrogen and helium. There's carbon and nitrogen and iron and silicon and all that. So where does that dust come from? It's the remains of earlier stars. And we'll see that they form heavier elements later. So there was a song many years ago called "We Are All Made of Stars." And I'm not worried about whether it's a good song or not, but the title is correct. All of the carbon atoms, all the nitrogen and the oxygen atoms that are in our bodies were once inside an earlier star that died. Because if you look at the color, the Big Bang really only made hydrogen, helium, and a little smidgen of lithium. All of these others were made by different stars. And I don't want to get too technical with it right now. I just want to make a point. I want us to think about iron, because iron is a very stable element, and we'll see that a little bit later, that most of the stars are only going to make up to iron in their normal lifetime. Now, is this stuff with planetary rings true? Yes. This is a star called HL Tau, and here's some evidence. Those dark bands that you see, it almost looks like Saturn's rings, but that's around a star. Those dark bands, there's no material there. That's where the planets are clearing out their orbit. That's why Pluto's not a planet, because it can't clear out its orbit the way larger planets like Jupiter and Saturn and all can. Now, we spent a lot of time in earlier videos looking at the planets in our solar system. But are there planets outside our solar system? Yes, those are called exoplanets. Exo, like exit, means outside. We've discovered over 4,000 so far, probably more since this video was recorded. Well, how do we do this? There's 3 ways. And the first is a Doppler shift. Now, what's a Doppler shift? We saw the Doppler shift, or we'll see it again when we talk about the expansion of the universe. We haven't seen it yet. It turns out that we say, okay, the planets go around their sun or their star. But what's more true to say is that the planets and the stars orbit a common center of mass. So if this is the star and it has a planet, we don't necessarily need to see the planet. But what we can see is when the star is moving towards us, the light that it emits is a little more blue. When the planet is moving away, the light that we see is a little bit more red. Now, a common place that you see the Doppler effect is when you hear, let's say, a fire truck go by. It's very high-pitched as it comes towards us, and then once the fire truck goes past our house, it kind of, the sound gets stretched out and is a lower frequency. So we know there's planets there if there's a wobble. If we see the star, the light changing, we can see that it's not just sitting there in space, it's wobbling a little bit. Now, that unseen planet, we call them hot Jupiters. We think they're really warm and really big, or about the size of Jupiter, if they're causing a wobble in our star. Sometimes we can actually see the star dim. It's very similar to an eclipse, which we talked about earlier. So if we look at the picture, as the planet would pass in front of the star, and if we look at the brightness, you see this dip here? That dip is a dimming, slight dimming of the star, which suggests that there's a planet there. Now, when the planet's in front of the star, some of the starlight is passing through the atmosphere, and we can even get an idea sometimes of what the atmosphere of that planet might be like if it has a gaseous atmosphere. And we use the Kepler telescope to look for that sort of thing. And you've certainly heard of Kepler earlier in this video series. In some rare cases, if it's a young, warm planet, if it's really warm, we can see them. We can get a direct image. Now, we can't see them in the visible range. But if we look at infrared, if you've ever seen an infrared picture, what it does is it detects warm spots. So in this case, and again, I just think this is an incredible picture, we can see that there are at least 4 warm little planets going around this particular star. So our solar system is not unique. There are other solar systems out there. Well, are any of them habitable? Maybe. It's sometimes called the Goldilocks zone, where it's not too hot, not too cold, and just right. And you can see from this graph here that some people have an optimistic habitable zone. They kind of allow a little wider range. And some people have a more conservative habitable zone and say, no, it's really only in this range here. So you can see Earth is just fine in the Goldilocks zone there. Mars is it's starting to get to the outside. So it has to be somewhere between Earth and Mars. Maybe Venus, we're not sure. Now, all these oddly numbered and oddly named little stars here, they're numbered and named based on the star they go around. So do they go around the TRAPPIST star? Do they go around the Gliese star? And it turns out that there's one in the habitable zone, only 4.2 light years from us, Proxima Centauri. That's a very, very near star. And it has a planet that could be in that Goldilocks zone. Now, some estimates. And there's an equation called the Drake equation that says, well, how many civilizations are there? But let's just look at possible habitable planets. In the Milky Way, might be up to 40 billion. And there might be 11 billion around sun-like stars. Now, does that mean there's 11 billion civilizations in the galaxy? Probably not. But there could be, on estimate, and again, this is an estimate, it's a model, up to 11 billion planets around a star that's a lot like our sun and is in the right zone. Now, moving away, let's go back to the stars and think about, well, how long do stars live? Here's a general factor. The larger the star, the shorter the lifetime. It's almost like some pop stars are one-hit wonders. They may be a huge star for a short while, and then they fade out and they never have another song or another popular movie, or they don't last very long. So it's really a battle between gravity, trying to compress the stars, and the pressure from the heat, trying to keep the star basically inflated, almost like a balloon. So remember that battle from a previous thing between gravity and pressure. Some really massive stars, like here's one that's 60 times the mass of the sun, only live about 3 million years. Our star, with a mass of 1, is expected to live about 10 billion years, roughly. So our star is halfway through its lifetime. Stars that are very, very small, they can live billions and billions of years, thousands of billions of years, and a bunch of the other ones are in between. But the bigger they are, the sooner they burn out. Now, main sequence stars are stars that are a lot like our sun. And what's going to happen to our sun at the end of its lifetime? It's going to become what's called a red giant. So here's the process. Stars fuse hydrogen into helium, and we're talking billions of years. That's what our star's been doing for 4.6 billion years, and will continue to do for another, almost 6 billion years. But eventually, you're going to run low on hydrogen. So it's going to now start to fuse the other elements. The star will contract a little bit and heat up and then expand. So the contraction is short. We're not going to worry too much about that. Just think about, we've run out of hydrogen. We've got to now start fusing helium. We're going to be making more and more heat. It will expand to a red giant. And some have said that it's going to expand out past the Earth and out perhaps even to Mars. So at one point, all the inner rocky planets, up to about Mars, may be actually inside the sun. So we have our sun small, and then it's going to be really, really huge. Well, on that outer spot is now the outer atoms are very far away from the center of the sun. Gravity, remember, the force of gravity goes down. It's an inverse square relationship. R squared is in the bottom. So gravity becomes very weak. It's going to lose a lot of its mass out into space. And a star that's doing this to show you a red giant is Betelgeuse, which is in Orion. You can see I have it circled over here. Betelgeuse has expanded as a red giant. If we draw these lines up here, it's so big, it's expanded well past the Earth's orbit out to about the size of Jupiter's orbit. So these stars, they start to run out of hydrogen, fuse helium, and expand, become very, very huge, a red giant. Now, what happens after them? So let's see. So these are lower mass stars, up to about 8 solar masses. So up to about our sun and 8 times as heavy. They will expand and form this red giant. And now they're fusing helium, and they'll fuse up to about carbon and oxygen. Well, at some point, they're going to run out of fuel too. They're not going to be able to fuse any more elements. And at that point, they're cooling down. Because they're cooling down, they don't have the pressure anymore, and they shrink. They will shrink to a certain point, which is called the electron pressure, caused by the electron pressure. Now, you may know from a chemistry class that electrons, some of them have what are spin up, and some spin down. And it turns out that you can't put 2 spin up electrons or 2 spin down electrons in the same location. So really, at a certain point, you can only contract matter so far, and the electrons will keep it from contracting any farther. So what will happen is, after it's a red giant, it'll shrink down, and it's about the size of the Earth, but it has 60% of the sun's mass. It's quite dense. That's a white dwarf. I think the graphic shows it very nicely, I hope, that it goes from a star to a red giant and then shrinks down to a white dwarf. Now, the white dwarf will eventually will shine due to heat. There's still heat in there, but it's not really undergoing the fusion anymore. So just like anything, if you took a hot loaf of bread out of the oven, it will cool down. The little white dwarf eventually will cool down like that loaf of bread. And there's immense pressure with carbon and nitrogen and oxygen. It's almost like a giant diamond, some people have said, for a white dwarf. And here's the white dwarf that's near us, Sirius B. You can see I have it circled there. Much, much smaller than that big star in the middle there. Some stars will go supernova. Once you get past about 8 solar masses, so we're talking in the 10 to 40 solar mass range, now they will do something interesting. They will expand too, and they become a supergiant. They're already big. They become a red supergiant. The process, and I'm going to show you a diagram of it in a minute, is very similar to what happens to a low mass star. But because they're heavier, they can fuse up to iron. You may remember that we said iron is special. We circled it on our periodic table. And this happens really, really quickly. Like we're talking in the range of months or days. We're not talking millions of years or billions of years here. And at some point, the fusion will stop and it will contract, exactly like we saw. Now, because it's such a heavy star, there's a lot more pressure. Before, we said, well, the electrons will kind of keep the white dwarf in place. There's so much pressure here that the electrons will combine with the protons. They just get squeezed together with the protons. And you remember that an electron is negative, a proton is positive. Well, positive and negative would cancel to be a neutron. But there's a byproduct. And that byproduct is a neutrino. We saw that in the video about the sun, that these neutrinos are released as a byproduct. It's the neutrinos that cause the supernova. Neutrinos are passing through the Earth right now. No problem. But in this star, if the neutrino is released from the core here, everything is very dense. So that fast-moving neutrino has to get rid of that energy somehow. And that energy gets absorbed by the outer layers of the star, and you get a supernova. You get this incredible explosion. With so much energy, we don't have to worry about iron. We have plenty of energy here to fuse all the way up to uranium. So all of the elements heavier than iron that we have on the Earth had to have come from the supernova. And you say, well, that seems weird. If you have a penny in your pocket with copper, or copper piping in your house, that atom had to come from the energy of a supernova because a standard star like ours doesn't have enough energy. Now, what remains is a little ball of neutrons, the neutron star. And we have plenty of pictures of these supernovas, but here's a picture just to show you, this is the remnant of what remains after the supernova. At the very center would be the neutron star, somewhere in there. We'll put it in, the neutron star. So here's a very similar picture to what we saw. But you see the star is bigger. So this is so what it does is it runs out of hydrogen, just like the smaller stars. Then it expands into a supergiant, a red supergiant, and it'll fuse up to iron. Once the fusion slows down and stops, it's cool, it has no more pressure, gravity contracts it to a neutron core. But the problem is there's neutrinos released, and they need to put their energy somewhere, and the star explodes. If it's in the range of 10 to 40 suns, you just have that neutron star there. And we'll talk a little more about those on the next slide. If it's greater than 40 suns, you could have a black hole. In fact, the black hole was just imaged in 2019, and you can see the picture up there. So the neutron stars, remember the ice skater. As she pulled her arms in, or he, they spin very, very fast. So these neutron stars are very, very compact and spin very, very rapidly. Now the neutrons are in the core. They do have some regular matter, some protons and electrons on the outside, which causes a magnetic field. And we can see it. It's something called a pulsar. So we can see these gas jets and light jets coming out of there. And the frequency they come out is radio waves. So it's kind of like a lighthouse. As the star is spinning, we can occasionally see the pulse. Much like a lighthouse, you only see the beam at certain times. And the black holes were imaged first in 2019. And they needed a lot of computer software. They actually used the computer language Python to get the picture of the black hole. So I think this summary chart shows it best. A low mass star, maybe 1 to 8 solar masses, will run out of hydrogen, swell up into a red giant, fuse some carbon and oxygen, and then eventually it loses some of its mass, shrinks down into a white dwarf. Heavier stars, once you get past 10 solar masses, they swell up too into that supergiant. But the supergiant can fuse up to iron. Then they're going to do the same thing. They're going to shrink back down to a neutron core. But the problem is neutrinos are emitted. And those neutrinos, they have a lot of energy, and they transfer that energy, and the star explodes. If the star explodes and it's lower, about 10 to 40 suns, it'll just remain as basically a big ball of neutrons spinning very, very fast in the sky. If it's very, very heavy, if it's so heavy, it will form a black hole. And the black holes are so heavy and they have such intense gravity that they bend space around them.